Welcome to Math 246, lectures number 24 and 25. And today we shall focus on disease modeling. We've spent 6 weeks discussing various aspects of population change, various kinds of models that we've discussed, and linear systems, nonlinear systems, which boil down to linear systems. And all of that is quite applicable in various facets of life, actually, in terms of how populations evolve, predator-prey problems, and so on. Those things were used to model such processes that take place all around us. Now, one of the most topical aspects at this time, of course, is diseases. In particular, the COVID-19 disease has struck the whole of humanity and has stunned the whole world because it paralyzed all of societies everywhere on the earth. And many of us would never have believed such a thing could happen. But of course, such things have happened before. This is not the first time we've had the whole world being paralyzed by a disease or by an epidemic. In the 1600s, 1665, in Britain, you had the bubonic plague. And this plague also harvested a big number of lives. And in 1918, you had the Spanish flu. So this actually is quite memorable because this is the time when people had proper records, some photographs and so on. And you can see what was happening in those days. And it was quite a complicated matter that took place there. Large number of lives were lost, and many of which could have been prevented had certain procedures been in place or had science developed to a level that we have it today. Now, these are what we call infectious diseases because you can infect other people. Allow me to speak about, firstly, about Daniel Bernoulli, mathematician. Daniel Bernoulli, around about 1776, part of the Bernoulli family, Johannes Bernoulli and Jacob Bernoulli. Johannes was a son, Jacob was the cousin, but the Bernoulli family were quite well-known mathematicians in Switzerland. And Daniel that is, he made many contributions to science, especially in the area of mechanics, the law of conservation of energy. Remember that from physics? Well, they trace it back to Bernoulli's ideas. And at his time, he worked with the mathematicians like Goldbach, who introduced the famous Goldbach conjecture in number theory. And he was also around at the time of Lagrange and others, famous French mathematicians. So in 1776, life expectancy, how long would you expect to live at that time? Life expectancy, would you believe, was 26 years of age. So if you are a student now, and let's say you are 20, 21, you only have another 5 more years to live on average if you were living in the 1770s because of the smallpox. The smallpox was ravaging lives all over the world. And so Bernoulli modeled smallpox development using mathematics. And based upon his models, he made an argument for inoculation or vaccination. Argument for vaccinations against smallpox. And in time, people took it up, most people, that is. In time, the life expectancy increased, shot up. 2, unfortunately, it only went up to 29. Actually, in past times, life expectancy was quite low. Life expectancy in our time has increased to a fair amount simply because of the quality of medical care, the advances in science, and the many diseases and sicknesses that are controllable and controlled and so on. Surgery can be done in many cases. So all these advances in science has actually increased the life expectancy of humanity. But if you had been living at that time in the 1770s, well, you'll get an extra 3 years in general. Of course, some people lived a lot longer, but how bizarre could it be that at that time, humans could only live up to 29 years of age? But in any case, that was only due to the intervention by Bernoulli and his mathematical models that he developed at that time. Now, he proposed this idea of compartmental models. This is exactly what is being studied even today, compartmental models. So you might have compartments, like you would have S, I, and R. I'll tell you what these means now. This is the SIR model. S stands for susceptible. In other words, susceptible means people who can get the disease, can be infected. I mean, that's everybody, right? Basically. I refers to those who are infectious. Sometimes they say infected, or some even say infectives. Infectives. And R stands for those who have recovered, but it could also refer to those who have died. So they are no longer in the picture. So people move from one compartment to another. So those who are susceptible become infected, and then some of them would recover. That's the basic idea of a disease model. Okay, or some would have the bad outcome, or they might die as a result of that. Now, when we model diseases, there are many assumptions. So this is why I think we said to you in the first lecture on mathematical modeling that mathematical modeling is not an exact science. It depends largely on all the inputs that you put into a system, but you can get very close to reality by tweaking the system somewhat as you go along, right? And some of the assumptions in disease models are one, everyone lives to a fixed age. Lives to a fixed age. So this is an assumption. In other words, there's a constant age distribution, which is not right. We know that, okay? Example, the age group 20 to 30. Same number as the age group 30 to 40, etc. So that is an assumption that's made in the model. That's how it is happening. But actually, we know the reality is false. Well, certainly in the bigger age group, 60 onwards, the numbers decline. 60 to 70 is certainly not anywhere near 20 to 30. So that's an assumption that's put into the model, and that can be factored in and can be mitigated as you go along by, developing the model a little more. But that is an assumption basically in these disease models, that the distribution of ages is constant across the levels. There's a famous statistics joke. Mr. Smith goes to his doctor, and Mr. Smith is 100 years old. So at the end of the examination, Mr. Smith asks his doctor, "So, doctor, how am I doing?" The doctor says, "You are doing fine. I'll see you next year." So Mr. Smith says, "But doctor, I'm 100 years old. How are you so sure that you'll see me next year?" The doctor says, "Don't worry, Mr. Smith. According to statistics, very few people die in the age group 100 to 105. So that's some comfort there for Mr. Smith. But anyway, it just shows you how statistics is an inexact science, and it can't be used very seriously in most cases, although it can give us useful information, but we have to consider all the factors more closely. Now, a second assumption here in the compartmental model is that the population is homogeneous, or we can say homogeneous mixing. People mix randomly. It's randomly, and not according to race or income, basically social groups. Now, this is a significant assumption in modeling of a problem mathematically, because in reality, this may not be happening. People might be mixing only with a certain crowd of people, let's say where they live. Uh, However, if there is a homogeneous mixing, then it's a simplification of the problem. Now, I can tell you, for example, modeling is also used in other areas of human life, like, say, insurance. Insurance is based upon a probability that you're going to die. Every month you take a bet with the insurance company that if you die, they'll give you 10 million. If you don't die, you give them the premium of 5,000 a month, whatever, for instance. Okay. So if you don't die, you lose your 5,000, but they regain the 10 million. If you die, of course, then they must pay you the 10 million, or you pay your survivors the 10 million. And in a sense, they lose. So it's a bet that you take on a month-to-month basis. Now, how do they calculate the probability that you will die? Based on many factors. For example, it's based on your age, it's based upon your habits, such as whether you're a smoker or a non-smoker. So the model will be tweaked accordingly. There'll be some factor that will be loaded on if you smoke, or if you have a precondition like diabetes or heart disease or whatever, then you buy your insurance policy late in life, then of course you will suffer the penalties that will come out of it. But there's also a question of social groups. And some insurance companies, and you guys who are studying at a university will become graduates one day. Certainly you will, you'll pass your courses. But there are certain insurance products that are geared towards graduate professionals. I'm not going to mention any names, but the idea there is that the rates that you pay are lower than what an average population would pay. The idea there is that people who are graduates drive better, more carefully, they take a better care of their health, they earn a little more than the average population, they can probably go to gyms, they have access to better healthcare. So their chances of living longer are better than somebody from a different social group, let's put it that way. So they factor that in. That's why you have to be very careful with the insurance products which say that no health questionnaire, no health, everyone can be accepted. When that happens, that means that the risk pool includes everybody. So even the worst risk cases are in that pool, and you, if you are healthy, will be paying to subsidize those cases. Okay? But then, of course, such a thing averages out, and everyone can be happily ever after. But be aware of products that consider the fact that certain risk pools are lower, and they give you accordingly a premium decrease because of that, or your money can buy more because of that risk pool. Right, enough for the adverts there. Let me now move on. The other thing here is that you're dealing with a closed group. Generally, there's no emigration or immigration. People are not coming in or going out. Now, with the COVID pandemic, you will realize we had lockdowns. The lockdowns was intended to keep people in one place, as it were, so that you don't move around too much. So when we say a closed group, it could either mean a closed city or closed province, closed country. When you close a country, basically you shut down the airports and on the borders, and nobody is allowed to come in and out. So these are the basic assumptions of the models that we use. Okay? Now, there are two types of models. Two types of models. Two types of models. One, we have what is called a stochastic model, a statistical model. Here, it depends on probability. What is the probability of somebody dying? And so it's based upon what we call random variables. And secondly, you have what is called a deterministic model. A deterministic model is where you have the movement from one compartment to another. one compartment to another. And the model is built using differential equations, rates of change, you see, using differential equations, not probability and random variables, but we use differential equations. And we also use certain initial conditions. Initial conditions. Remember the predator-prey models, we could start off anyway. We could say, suppose there's 30 buck and 20 lion or whatever it is in a certain area. That's an initial condition, right? Here, we could have initial conditions also, many parameters. There are many parameters, example, alpha, beta, gamma, etc. These are specific for a disease, specific for a certain disease. For example, measles might have a certain alpha value, infection rate. Yeah, usually these are like infection rates or death rates, for example. Okay? So measles might have a certain infection rate, smallpox will have another one, polio might have a different, COVID-19 might have a different alpha. So these are the different considerations there. Then I must also mention the thing called reproduction number, which you have heard a lot of in the news. Reproduction number. I will derive this shortly, but at this time, let me just say what it is in the broad framework of disease modeling. A reproduction number is a number indicating if a disease becomes an epidemic or it dies out. It's a number indicating if a disease becomes an epidemic, in other words, carries on increasing, epidemic, or it dies out. It can also become endemic. Endemic. Endemic means that it's a constant position. Constant position. It's not improving or worsening. So that we say endemic. For example, people might say corruption is endemic. That's where they use the word often. It means that in certain circles, people are generally corrupt. Things balance out, and that you know you can't get rid of it. It's always there. Okay? All right. Now let us consider some disease models. So some disease models, starting off with the simplest and working our way up to the more complicated ones. Some disease models. So firstly, let's talk about the SI model. SI model. Susceptible and infective. Right. So here we have only two compartments. Only two compartments. Susceptibles that become infected, and nothing else happens after that. In other words, they remain infected. Okay. So what disease can you think about that has this position? There's no cure, basically, right? So in other words, diseases such as HIV, people remain infected. People remain infected. Question. The flu, okay, but the flu you can recover. There is like vaccines can help you, or natural immunity kicks in, and after a couple of days you get out of the flu. Okay? But the SI model diseases where there's no cure, basically, like HIV. So once you get infected, you remain infected until somebody finds a cure. Now, the assumption here is that the rate of infections, and this is a common assumption for all these models, rate of infections is proportional to the interactions. What is this word? To the interactions between the susceptible and the infected or infective. Okay, so this is an assumption. Remember the predator-prey problems? We had the X, Y in the problem. That represented the number of times the buck and the lion could interact. And of those interactions, some of them will result in an eating, where the lion will eat the buck. So there was a certain number, beta or alpha before XY, like alpha XY or 2XY or 0.2XY, meaning that 0.2 of those interactions result in a case where the buck is eaten by the lion. Likewise, when a susceptible person meets an infected person, they could get the disease. Not that HIV works that way, by the way. It doesn't actually. But I'm just saying that this is how it works, the model, right? So you have susceptibles, and they move into the compartment called infected or infectives. And the number that does this is proportional to the interactional. So the interactions are S times I, SI. And the proportion, let's say, is beta. This beta is a free parameter. Is a free parameter that is like basically the infection rate. And it varies from disease to disease. It varies for different diseases. Okay, and this model here is what we call a one-way model. Someone from I cannot go back to S. Someone from I cannot go back to S. Right, so I think we already said that it's a closed model. Now let's see how the mathematical model looks. The mathematical model will be of the type, the rate of change of susceptibles, ds dt, will be, okay, the number of interactions is SI, right? And then we said there's a proportionality constant in front of that. It determines the rate of infection. And of course, it'll be the rate of change of the susceptible will be negative because it'll decrease. Right? On the other hand, if you take the di dt, the rate of change of the infected, they will be increasing by the same number. Okay? Those guys will move from the S category into the I category. So the rate of change there will be beta S times I. So that's a very simple model. The rate of change ds dt goes as minus beta Si. All right, so what we can note here, and this is going to happen all the time, that the sum is, if you add the two up, ds dt plus di dt, you will get 0. And both are dt, so d dt of s plus I is 0. This means that s plus I is always the constant, or s plus I equals to n, where n equals to total population. But remember, this population n could either be for a locality, it could be for a town, it could be for a city, it could be for a province, it could be for a country, or it could be for the whole world. Okay, but the fact is that s plus I is always equal to n. Right? S plus I is always equal to n. So model can be understood as a one-dimensional model. If you think about the fact that ds dt, well, let's look at di dt. Di dt, that's what is important, right? The infected. Di dt we said is beta si. But now we have learned that s is actually n minus I. So we can say di dt is equal to beta I into, sorry, this is n minus I, into n minus I. Now, what kind of a model is that, guys? Di dt is beta I into n minus I. Surely you've seen that before. That is an example of a logistic model. Logistic model. You see, using this result, s equals to n minus I, which I'm going to use a lot in the discussion hereafter, I can reduce the number of equations from 2 to 1. So I brought it down to a one-dimensional system. I can reduce the order of the system by 1. So the logistical model is what we have here. Okay. It's I dot equals to beta I n minus I. Sorry, n is a constant. It's like x into 1 minus x. Wasn't that the logistical model? So that means the way this disease operates is logistically. It starts off from some way, increases, and then it tapers off to some number here, which let's say is n. We used to call that the carrying capacity. But basically the infectives, this is I versus T. The infectives head towards a constant position, a stable position like that. That's really what's happening. Okay, now a modification of this. By the way, let me label these according to the notes. We've got notes there for you. In the notes that we have given you there, I think the SI model is called 4.1. Let me follow that labeling in case you read the notes in parallel with these lecture notes. So 4.2 now, it will be a modification of that. This is now the SIS model. Now in the SIS model, some infectives recover and become susceptible again. Well, example, COVID-19, we know that people can recover, but people can get infected again. So it is possible to get reinfected. And of course, when you get infected once, you develop immunity against the disease, or your body learns to fight it. So if you get infected again, you would expect to have a lower form of the disease. It wouldn't be as devastating as the first time around. If it was, remember the first time around also could be very low level. Most people won't even have symptoms and wouldn't have known that they had it. I think this is also what's happening in the population. Many of us may have had it without even knowing it because the symptoms were so low key that we didn't realize it. In other words, we didn't have to go for the test or go to a hospital or anything. So in this kind of model, you have susceptibles, the compartment here. They become infected. And then some of the infected move back here and become susceptible again. So the number that move from S to I, or the rate of movement, is beta Si. And let's say of the infected, some go back into S. Well, how many? Let's say a fraction of I, gamma I. So gamma A is a new parameter now, some new parameter, which refers to recovery. It's like a recovery rate. So it's a new parameter like a recovery rate. So now, what is a model? Let's now look at the way the model can be written. The model will be ds dt, the rate of change of the susceptibles is again minus beta si. And this is how it starts. di dt is beta si. Those guys who are infected from the first one go into the second model. But now, some of these guys in the second category, a fraction of them, the fraction of the infected, is removed and they go into the first category. So the model becomes minus beta si plus some gamma I, whereas the lower one is beta si minus gamma I. Again, if you look at the sum, conservation here, ddt of s plus I, add everything up, you'll get a 0, which tells us that s plus I again equals to n, right? Constant. The number of susceptibles and infected is remaining constant. Okay, so you see the assumption here is that there's no one being born in the system and there's no one dying in the system. Now, if you want to take into account new people coming in, we already said it's a closed system. There's no immigration or immigration, but in the system, we have people being born and some people dying. The rate is quite different. So we are not taking that into account. It's a simplification that we have in this model. Now let's go on to the one that's very important and the one that's currently in use for the COVID-19 infection is the SIR model. This was created by Kermack and McKendrick. In the early part of the last century. And it's quite an efficient model, you see, because here we have, so the assumption here is that individuals, let me just write this down for you, individuals recover or they die, so they are removed. They are removed and no longer infectious. Also cannot be infected again. Infected again. In other words, they are immune. Technically, they are immune. This is not the case with COVID, but it's a reasonable assumption that can help us to get some idea of how the disease progresses. Okay? It has been assumed in this way. Now, so we have S, we have I, and now we have a new category called R, recovered, or has died. So the number or the rate of the people moving from one to the other is beta Si again. And from I to R is some gamma I. This fraction of the I becomes R. So based upon that, we can devise the model ds dt, or we can say S dot, by the way, is minus beta Si. Di dt is beta Si minus gamma I. And lastly, we can have dr dt. The people in the last compartment are the other gamma i's that moved across. Okay. So again, notice that the sum is 0, which means that S plus I plus R gives you N. And you have 3 equations here. You have 1, 2, 3. But using the fact that N is equal to S, or rather S is equal to, let's rather use the fact that, because N is a constant, see? Using the fact that S is equal to N minus I minus R, or R equals to N minus S minus I, we can have a two-dimension system. We'll do an example of this later on to see how this works in practice, but you can reduce the order from 3 equations to 2 equations using the fact that the 3 items are related in that manner. All right, let me just finish up with these disease models before coming back to an actual problem. I think this may be the last of these disease models, SEIR. SEIR model. In this case, E stands for exposed. So you have E means people infected, but not yet infected, infectious. Infected, but not yet infectious. An example of this is TB. Some immediately can infect, some later. Some can infect immediately. And some later. So TB is an example of this kind of stuff. So here you would have these compartments, S going to E. These are going to be exposed to the disease. E going to I. And R are the recovered or the persons who have died. So the people going from S to I, the rate is beta SI, as usual. Then some alpha E go into I, and from I to R, some gamma I go to R. So the model will be written like as follows. We have, let me use the, let me use S dot is equal to minus beta SI. Then E dot will be beta SI, those same guys that came from the first compartment. And some of them go into the next compartment, minus alpha E. Then I dot, the third compartment, accepts those guys and loses some guys to R. So R dot is simply gamma I. So now you have 4 equations. 1, 2, 3, 4. But 3 are independent equations. Independent equations. Since we know that S plus E plus I plus R is constant. We're calling it N in these models. Okay, so there we go. Now that's the kinds of models. So that's the different types of models that are in existence, and each of those can be tweaked, can be modified depending on the situation and what you want to achieve and how you understand the disease. As I mentioned, a lot of the disease modeling is done post facto. After the disease has passed, then you analyze the data and see what kind of model would fit that data. And then the next time a similar disease appears, then you can then have some way to predict how the outcome is going to be. So it's a bit learning from the past, basically. Now let's come back to this number, reproduction number. Reproduction ratio, R naught. So you may hear television epidemiologists mentioning this reproduction ratio. If this number is more than 1, well, let me define it. R naught is the average number of secondary infections. Average number of secondary infections. In other words, you get infected, you can infect somebody else. Secondary infections produced by a single infected person. By a single infected person. In a totally susceptible population, in a totally, let's include all this, totally susceptible population. In other words, everybody has an equal likelihood of being infected, which is not the case if people have taken a vaccine, right? That's why the modeling has to be always tweaked to account for all the changes that take place in the environment. Now, if R naught is positive, is more than one, sorry, then it reaches an epidemic. Each person infects more than one. So if you have a disease and you infect two people, those two people infect another two people each, that's 4, then it becomes 8, 16, increases exponentially. So that becomes an epidemic. On the other hand, if R naught is smaller than 1, then we have the disease dying out. Disease dying out. Or there's a cure being found, or possibly there's a vaccine being introduced, or people's habits have changed, like such as in the lockdown, etc., etc. There are many ways. So we are actually wanting R naught to be less than 1 when we have a certain disease at hand. If you have R naught equals to 1, this is the case of the endemic state I said earlier on, endemic, what we call a stalemate. There's no movement. See, I wonder whether COVID-19 will reach the stage where there will always be a certain number of people dying and it won't be eliminated entirely. But we'll have to see how it goes. Okay, so that's a reproduction number. So let's now calculate this. So consider the SIR model, where all are fully susceptible. In other words, there's no one with a vaccine susceptible. And S at the beginning is N, the total population. At the beginning, so at start, at beginning, S is N, infected is 0, and the recovered, of course, is 0 because there's no disease yet. It's in the start. Now, introduce one infected person. Introduce one infected person to the system. Person in the system. In other words, put I equal to 1. So note, if di dt is positive, the rate of infection is positive, it means that the rate is increasing. It's increasing and it's reaching an epidemic. So we would like di dt to be less than 0, to be negative. So we have, recall from the above, di dt is equal to beta si from the model minus gamma I. Remember the model SIR, S going to I going to R. Here it was beta Si, and here it was gamma I going there. So that was the model there. So if di dt is positive, this means that beta Si minus gamma I is positive. And here we have that the S susceptibles is the whole population N at the beginning, and we have I equals to 1. We put one infected guy in. So beta Si will become beta N. I is 1, S is N, so beta N, minus gamma I is 1 more than 0. So then we get beta N more than gamma. And so finally we get beta N over gamma is more than 1. It's all positive, you see. You can take the gamma across. So it is convenient. It is convenient to define R naught to be beta n over gamma. So if R naught is more than 1, it implies epidemic. If R naught is less than 1, it implies disease dying out, declining. So this is the famous reproduction number. R naught is defined as beta over gamma times n, the population number. Remember, beta is the infection rate and gamma is the recovery rate. Beta is the infection rate. This has to be obtained experimentally, and gamma is the recovery rate. That's why I said a lot of the disease modeling is accurate after the fact, after you know all the how the disease has progressed. Okay, so that's that number there. Now, you probably are wondering, can you solve for I in terms of S or S in terms of I and so on? Okay, let's see if we can do that. Solving for I in terms of S. We've got differential equations, you know. Can we solve the differential equation in some way? If you remember, the model is S going to I going to R. Beta Si is a rate there, gamma I is a rate there. And the model is S dot equals to minus beta Si. I dot equals to beta Si minus gamma I. And R dot is gamma I. Now, we know that S plus I plus R is equal to N. Right? Also, di ds, if I take di ds, it will be di dt divided by ds dt. In other words, I dot over S dot. I dot is beta is minus gamma I and over minus beta is. So that's the differential equation. Now we have di ds. I can divide this by beta is, so it'll become minus 1 here, and plus gamma. So the i's will cancel out. It'll become gamma over beta s. So there we go. The differential equation, we have I expressed in terms of S. So it may be possible to solve this. So if we integrate this with respect to S, we'll get I equals to integrate 1 is minus S. Integrate, remember this is gamma over beta S is like gamma over beta times 1 over S. So it's gamma over beta. Integral of 1 over S is ln S plus some constant. So there we go. That is the form of the I in terms of S. It's possible to do it. But we can't find S explicitly. We cannot find explicitly S in terms of I. Can't find S in terms of I explicitly, the other way around, because the equation is not algebraic. It's got a log in it. So it can be given in terms of some special functions. And in this case here, there's a function called W function of Lambert. You may have come across some special functions in other studies in mathematics, but there are many special functions like the Bessel function, even the Legendre function, and so on and so on. Right? So there is a certain function called the W function of Lambert, and we can write the solution in terms of that. Okay, so we succeeded in doing that. Now, in conclusion, let me take an example. So in this example, we'll have an SIR model. The model will be of the type, of course, S dot equals to minus beta SI. By now, you should know this off by heart. I dot equals to beta SI minus gamma I. We can ignore the third equation. Remember, I said that you can reduce the order to 1. Right? Say the initial conditions are as follows. Initial conditions are S at naught is equal to 0.9. In other words, 90% of the population is susceptible at the beginning. Also suppose I of naught is 0.1. 10% are already infected. And the parameter values for this particular disease are beta equals to 2 and gamma equals to 0.5. So we have to know this information up front before we can actually write down the model. So then the model can become S dot equals to minus 2 SI, because the beta is minus 2 now. I dot equals to 2 SI minus 0.5 I. Okay, so now if you look at that, okay, if we put, let's say S to be X and I to be Y, you've got X dot equals to minus 2xy, Y dot equals to 2xy minus 0.5 y. X dot equal to that. Now, does this not ring a bell? Are you able to do this? Definitely you can do this because we have done more complicated problems in the past. You see, in the past, we had things like x into x, x into 1 minus x minus, say, 2xy. So that was a competition model, a predator-prey model. So this is very similar. This is a nonlinear system. It's a nonlinear system. And we can reduce to a linear system. Using the Jacobian. We can find the eigenvalues. And then we can determine the quality of the stability at the fixed points, wherever the fixed points are. So the game, let the games begin. We now know how to handle this, right? Let the games begin. So we have built up the machinery to be able to handle a nonlinear system, to analyze it in detail, and to find the solution trajectories for the nonlinear system. But it will take us some time to do that. So let me stop here so that we can deal with that in the next lecture.